So in this module, and in fact in some of the modules that are going to follow, what we will look at is a slightly different kind of stochastic process compared to what we have seen so far. So we'll be looking at what is called a counting process. Essentially, it's a situation where some event or arrival would take place at random points of time, continuum in the continuum. That means in the whole time interval from 0 to infinity, and the process would simply record the count of number of arrivals up to time t. So we start with a general definition of a counting process, and then we specialize to one special counting process which is of enormous importance in applications into queuing theory and many other areas, namely that of what is called a Poisson process, or more correctly it should be called a homogeneous Poisson process with intensity or rate lambda, and examine. First we start with the definition and then examine some of its properties. First I start with counting processes. So basically you want to model a situation where, let's say, a particular event of interest keeps on occurring repeatedly at random time points over the whole non-negative continuous time horizon. We call it capital T, which is basically 0 to infinity. So all possible non-negative times. Typical examples would be road accidents at a particular spot, so they keep on happening at random times. Emission of radioactive particles from a substance, so the emissions keep on occurring repeatedly at random points of time. Hits of a specific website, so again a particular website may be hit at random points of time, so it's the same events that keep on repeating. And a very common example is arrival of customers at some service counter, and this has a lot of applications. Okay, so you have random occurrence of occurrence times of the successive events, so we would denote them by S1, S2, S3, etc., Sn. So the S1 is the time of occurrence of the first event, S2 is that of the second event, and so on and so forth. So in general, Sn is the random time of occurrence of the nth event, n greater than or equal to 1. So Sn's are non-negative real valued random variables, satisfying this inequality that Sn has to be less than or equal to Sn plus 1, because Sn is the time of occurrence of the nth event and Sn plus 1 is the same for the n plus first event, so they must be ordered this way. But the important thing to notice is that at this point of time equality is allowed, so which means that as of now we are not ruling out the possibility of more than one occurrence taking place at the same time point, which is why Sn could be allowed to be equal to Sn plus 1. That means the nth and the n plus first event may occur at the same time. For the sake of completeness, we'll put S0 to be identically 0. So, including S0 in that chain of inequalities, this is what we have. 0 equal to S0, less than or equal to S1, less than or equal to S2, etc., etc. So now we are going to make a very, very important assumption. Without this, the entire theory would collapse. Very, very important assumption is that we assume that Sn goes to plus infinity as n goes to infinity with probability 1. So what does that mean? That really means that only finitely many occurrences with probability 1 in any finite interval. Because if you give any finite interval, it cannot be that all the Sns lie in that interval, because Sn has to go to plus infinity. So only finitely many Sns would be lying in that interval, which essentially means that only finitely many occurrences in any finite interval. So there is no explosion of number of occurrences in any finite interval. Okay, so what is counting process? It just counts the number of occurrences over time. As time advances, we keep on counting how many occurrences have happened until that time. So here is a precise definition. For each t in that time set, we denote nt to be the number of occurrences or events up to and including time t. So it's a number of occurrences during time interval closed 0 to t, both included. Equivalent definition is that nt can be thought of as the maximum of all n's greater than or equal to 0, such that Sn less than or equal to t. So you can convince yourself that that essentially defines the same thing, that is the number of n's. So when you take the maximum, that the value of that maximum gives you the number of n's for which Sn is less than or equal to t, or equivalent to the number of occurrences. Okay, so note that the fact that S0 is taken to be identically 0 and Sn goes to infinity with probability 1 will imply that for any t, fixed t, the set n greater than or equal to 0, Sn less than or equal to t is non-empty. That's because we are allowing n to be equal to 0 and S0 is always less than or equal to t because S0 is 0. So it's non-empty and bounded above because it's not possible that all the Sns for every n is less than or equal to t. That is because Sns are supposed to go to infinity. So this is a finite non-empty set and therefore it has a maximum. So NT is well defined. So this process NT is called a counting process on R plus, which is just this time set 0 to infinity. So counting process can be thought of as a stochastic process with continuous time parameter set. So the random variables NT are indexed by t, where t can take values in the whole continuous parameter set 0 to infinity, but the state space, that means NT can take values in only S, which is Z plus, which is the set of non-negative integers. Also from the definition it should be clear that this process, which I denote by NT t greater than or equal to 0, has non-decreasing paths. That simply means that for any two time points S and t with S less than t, Ns has to be less than or equal to Nt. That's obvious because the number of events up to time S cannot exceed the number of events up to time t if S is less than t. So from the definition of NT, you can easily see that if you take any two time points S less than t, then the increment of the process NT minus Ns would represent the number of occurrences in the interval open S to close t. So S is excluded because Ns is subtracted, which means any event that might have occurred at time S is not included here. So it counts all the events that occurred during the interval S to t, S excluded but t included. Also, if you fix any t positive and n greater than or equal to 1, then you can see that nt greater than or equal to n, that event, meaning that at least n events have occurred up to time t, is the same as Sn is less than or equal to t. That is, the time of nth occurrence is less than or equal to t. Of course, by looking at the complement, nt less than n, which is same as nt less than or equal to n plus 1, because nt only takes integer values, would be equal to complement of Sn less than or equal to t, which is Sn greater than t. From which you can easily see that nt equal to n would be the event that nt is greater than or equal to n but less than or equal to n plus 1, less than n plus 1, or less than or equal to n, from which you get that these two events are same. In particular, SNT is the time of occurrence of the nth event, which is the last event up to time t. That has to be less than or equal to t by definition. And the SNT plus 1, which is the time of occurrence of the event which is to happen after time t. So that, of course, has to be greater than t always. That's clear from definition. So, of course, the counting process is completely determined by the sequence of successive occurrence times, because the entire randomness comes from there. Therefore, if to be technical, if I have a probability space omega fp on which a sequence Sn of random variables is defined, then the process Nt is also defined in the same probability space. This is just a technical remark. Now it's clear from the definition that for each omega in omega, the function t going to nt omega, the fixed in omega, look at the function t going to nt omega. So this is a function of 0 to infinity. This is often called the omega path or omega trajectory of the counting process. It's going to be a step function on 0 to infinity, non-decreasing and right continuous with integer jumps at these times s1 omega, s2 omega, etc., etc. This is illustrated in this picture. So you see that this is a typical trajectory of the counting process. So at time points s1, s2, s3, there are jumps. Between these two, the trajectory remains fixed, constant. So step function. Now I come to the special, very special counting process, namely Poisson process. So as I said, the Poisson process is a special counting process, and here is the definition. A counting process Nt is called a Poisson process with rate, sometimes also called intensity, lambda, if first of all n0 is identically 0, and b, for any choice of time points t1 less than t2 less than etc. tn. So take any finite set of time points ordered in that fashion. Then the random variables nt1, nt2 minus nt1, etc., ntn minus ntn minus 1 are independent. So roughly what it means is that nt1 is the number of events up to and including time t1, nt2 minus nt1, that increment, is the number of events occurring in the interval open t1 to close t2 and so on. They are assumed to be independent. And the last condition is why it's called Poisson process, that for s less than t, nt minus ns, that is the number of events occurring during the interval open s to closed t, that random variable, which of course is non-negative integer valued, the distribution is Poisson with parameter lambda into t minus s. So property B is often expressed as the property of independent increments. That's clear. We are saying that, if you fix a finite set of time points, look at the increments over those time points, then they are independent. Property C is why the process is called a Poisson process, because the distribution of nt minus ns is Poisson, and it's called, this is why and since the lambda parameter is coming there also, this is why the process is called a Poisson process with rate or intensity lambda, and we are going to frequently abbreviate it as pp lambda. So pp lambda would stand for a Poisson process with rate or intensity lambda. Now let's see something more that the property C says. Property C says that, in particular, that if you take s to be 0 in property C, then nt minus n0, but n0 is by A defined to be 0, so it says that nt is Poisson with parameter lambda t. Okay, so the number of occurrences up to time t, starting from time 0, that random number is distributed as Poisson with parameter lambda t, and from this you see that for any s less than t, the distribution of nt minus ns, which is according to C supposed to be Poisson with parameter lambda t minus s, but this is also the distribution of lambda n at t minus s. So the distribution of nt minus ns is same as the distribution of n t minus s. What it says is that the distribution of the increment over a time interval st really depends only on the length of the interval, does not depend on where it's located. So a property often expressed as property of stationary increments. Here's an important property. If you fix an s and define a new process to be called n tilde t, and define it as for every t greater than or equal to 0, it's defined to be ns plus t minus ns. So s is fixed here. So it's a process over t. Then the fact is that this new process nt tilde is again a Poisson process with intensity lambda. So it's exactly like the original process. Moreover, it's independent of nu for u less than or equal to s. So let's see why it's true. It's actually a consequence of the definition. That this new process nt tilde is a pp lambda is immediate from definition, because n0 tilde is clearly 0, and the increment of nt tilde over a time t to t prime is exactly the same as the increment of nt over the time interval s plus t to s plus t prime. You can easily see that from definition, from which the other two properties follow immediately, because to check properties of the increments of n tilde, you have to really go back to properties of, because they are increments of n as well, and therefore properties of increments of n tilde follow from properties of increments of n. So therefore it turns out that nt tilde is exactly once again a Poisson process with same parameter lambda. Now to show that this nt tilde process is independent of these random variables nu, it's enough to show that for any collection of finitely many time points u1, u2, um less than s, and t1, t2, tn greater than s, the random vectors nt1 tilde etc. ntn tilde and the vector nu1 etc. num ns are independent of each other. Or equivalently, I can look at the from the set nt tilde etc. up to nt tilde n, I can, rather than showing that that vector is independent of this nu1 etc. ns vector, it's enough to look at the increments of this vector. So nt tilde, nt1 tilde, nt2 tilde minus nt1 tilde etc. and similarly increments of the other vector. It's enough to show that these two vectors are independent, because once you show that these two vectors are independent, the original vectors can be written as partial sums of these vectors. Just convince yourself. But this is now an immediate consequence of the independent increments property of nu. Just verify this, because this increments of the nt tilde process can be written as increments of the n process, as we've already seen, and then the whole thing becomes just a property of increments of the n process over disjoint intervals. Okay, so just write down and verify this. And that's what I've said. So this is an immediate consequence of the independent increments property of NT. Here is what this property that is just now proved says. So if you have a counting process NT, which is a pp lambda, then fix any s positive. For such an s, the counting process NT tilde that we have defined, that counts the number of occurrences starting from time s onwards. That's exactly what, if you look at the definition of NT tilde, that's exactly what it does. It's as if whatever has happened up to time s is not not brought into picture at all. You start counting, your time starts at time s, and you start counting the number of events starting from time s onwards. Then this process behaves exactly like the original counting process, and it's independent of the occurrences up to and including time s. So one way to think about it, that if a Poisson process has been running, but you happen to enter the picture only at time s, and for you the process starts at time s, then this process that you are observing is also a Poisson process, exactly like the original process. It's independent of all the past that already has happened up to time s. Okay, now we turn to an important question. Recall that the definition of a general counting process was based on repeated occurrences of an event at random points of time, and denoting Sn, n greater than or equal to 1, to be the random time of the nth occurrence, and putting S0 identically equal to 0, we have the sequence that we have seen already at the definition of counting process. And we assume that Sn goes to infinity as n goes to infinity, and define the counting process Nt as Nt is the number of occurrences during the time interval 0 to t, or equivalently Nt is, so as was seen when you define counting process. So a natural way to define a specific counting process, which as I said Poisson process is, would be to first specify the sequence Sn, that is to specify the joint distribution of the sequence Sn, and then derive the distribution of Nt from there. However, that's not what we did. We defined a Poisson process with rate lambda by directly prescribing the distribution of the counting process Nt, and without any mention of the underlying sequence Sn of arrival times. Question. From this definition of this counting process Nt, which is a Poisson process with rate lambda, what can you say about the joint distribution of the arrival times for the Poisson process? So that's the question that we're going to now look into. So let Nt be a Poisson process with its sequence of successive arrival times denoted by 0 less than or equal to S1 less than or equal to S2, etc., etc. Now, using the definition of Poisson process with intensity lambda, we are going to explicitly find the joint distribution of S1, S2, Sn for every n greater than or equal to 1. So let's start with distribution of S1 first. Note that because our definition of Poisson process says that n0 is identically 0, that immediately tells you that S1, the time of the first arrival, has to be strictly positive. No arrival at time 0. That's part of the definition of Poisson process. Next, by definition, S1 greater than t, that means the time of arrival of the first event, is strictly larger than t, means at time t, up to time t, no event has occurred, so nt equal to 0. That is same thing as saying that S1 less than or equal to t is the same as the event that nt is strictly positive for all t greater than 0. Now we use the fact that in the definition, from the definition we know that nt is for a Poisson process is a random variable with distribution Poisson with parameter lambda t. What we immediately get is that the probability that nt is positive is 1 minus e to the minus lambda t, because for a Poisson random variable with parameter lambda t, the probability that it's 0 is e to the minus lambda t. So 1 minus e to the minus lambda t is the probability that nt is greater than 0, so that we get probability that S1 is less than or equal to t is 1 minus e to the minus lambda t, but it's easy to see that that is nothing but the integral 0 to t lambda e to the minus lambda is ds for every t positive. So that tells you what? This is the distribution function, cumulative distribution function of S1. So that cumulative distribution function at t is the integral from 0 to t of this function lambda e to the minus lambda s ds. So this suggests that lambda e to the minus lambda s is the density of the random variable S1, which is a familiar density. It's called the density of the exponential random variable or distribution with parameter lambda. So we conclude that S1 has distribution exponential with parameter lambda. So having obtained the distribution of S1, now the next step would be to find the joint distribution of S1, S2, Sn. So what we need for this is a very basic result from probability, which is this lemma. Suppose y1, y2, yn, I call it bold-faced y, be a random vector taking values in some region G in Rn. So it's an n-dimensional random vector. Suppose I have a non-negative function h on G such that for every rectangle, that means a set of the form a1 to b1 open in the left, closed on the right, cross, etc., etc., an to bn again open on the left, closed on the right. Suppose you take any such rectangle contained in the region G, then the probability that the random vector y lies in this rectangle, which simply means that y1 lies in a1 to b1, etc., yn lies in an to bn. Suppose that probability equals the integral of the function h y1, y2, yn over this rectangle. So this is a multiple integral. That's really the integral of h over that rectangle. Suppose this is true for every rectangle contained in G. Then y has a joint density given by h. That means the function h must be the joint density of y. Of course, since y takes values in G, the density is h on G and 0 outside of G, joint density. So now let's get to our original question of finding the joint distribution of S1, S2, Sn. Let's do the case when n equal to 2, just for the sake of simplicity. So I look at only S1, S2 and I want to find the joint distribution of the pair S1, S2. Now by definition S1 is less than or equal to S2. So the pair S1, S2 takes values in this region G, namely the set of points little s1, little s2, where little s1 is greater than 0 and s1 is less than or equal to s2. Now what I do is I'm going to apply that lemma, take any rectangle which lies in this region. So that simply means that I am taking any one a1, b1, a2, b2 in that order. Any such rectangle with a1, b1 cross a2, b2 will lie in that region. So I try to calculate the probability that s1, s2, this pair lies in that rectangle, which, as I said, is the same as s1 strictly bigger than a1, less than or equal to b1, and a2 strictly less than a2, and s2 is less than or equal to b2. Remember, s1 is the time of the first event and s2 is the time of the second event. So this event can be written in terms of the original Poisson process as follows. So saying that s1 is greater than a1 simply tells you that n a1 is 0, no event up to time a1. Then saying that s1 lies between a1 and b1 with equality allowed at b1 simply tells you on the time interval a1 to b1, open at a1, closed at b1, exactly one event has taken place. So n b1 minus n a1 equal to 1, and that is because s2 is bigger than a2. So n a2 minus n b1 is 0, and then the last condition that s2 is less than or equal to b2, greater than a2, tells you that n b2 minus n a2 is greater than or equal to 1, greater than or equal to, because we do not know. It may be that s3, s4 also may be less than or equal to b2. So we only know that s2 is less than or equal to b2. So there may be more events than just one in the interval a2 to b2. So anyway, so this probability is same as this probability. Now the advantage is, once we have written this event in terms of the Poisson process, or more specifically the increments of the Poisson process, we can now go back to the definition of the Poisson process and use the properties. So independence of increments and that third property, that stationarity property. First we use independence of increments to write this probability as a product of 4 probabilities, and then use the stationarity. So you can write down these probabilities explicitly because they are all Poisson distribution probabilities, and then do some algebra, and this is what you get: lambda b1 minus a1 into e to the power minus lambda a2 minus e to the minus lambda b2. But the point is that you can easily see that that turns out to be this double integral. Remember, the lemma tells us that we should try to be able to write the probability of s1, s2 lying in that rectangle, two-dimensional rectangle, as a double integral over that rectangle, and that's exactly what the last expression does. And the moment you have that, you immediately know what is the density, joint density of s1, s2. So using the lemma, we conclude that the pair s1, s2 has joint density given by this: lambda square e to the minus lambda s2 as a function of s1, s2, as long as s1 is positive and s1 is less than s2, and 0 otherwise. Now, case n greater than or equal to 2, well, it's not so difficult. For any n greater than or equal to 2, the vector S1, S2, Sn takes values in this region, exactly as we did in the previous case. So following the same arguments as was done in the previous case, you can show that for any rectangle in the region G, the probability the vector S1, S2, Sn lies in that rectangle, which is exactly the probability written in the first left hand side. And again, you can convert this into an event in terms of the NTs and their increments, and then use the definition of the Poisson process, simplify, and this is what you get. Now we have to somehow try to think of this last expression right hand side as an n-fold integral of some function of n variables. Then that function would give us the joint density. So that's not difficult. You can show that this right hand side is indeed the integral over the appropriate rectangle of this function f S1 S2 Sn for S1 less than S2 less than Sn, all positive. The function is this and 0 otherwise. So therefore this must be the joint density of S1 S2 Sn. So what have we proved? We have proved that S1 has exponential lambda distribution, and we've also obtained the joint density of S1 S2 Sn for every n greater than or equal to 2. Now from the formula of joint density, it is not yet clear exactly what is the joint distribution of S1 S2 Sn. We have a formula for the density, but we'll see get a better picture very soon. Of course, the marginal distributions of the successive arrival times S2 S3 can easily be obtained from these joint distributions. That is something you know. If you have the joint density, you can find out the marginal density by integrating out all the other variables. But let's now consider a slightly different sequence of random variables, which are going to be extremely important, called the successive inter-arrival times, which will not only give us a better understanding of the successive arrival times, but will also present an alternative way of looking at the Poisson process, as we will see later. So let me first define what the inter-arrival times are. So they are random variables xn, again a sequence xn for n greater than or equal to 1. They're defined like this. x1 is s1 minus s0, which of course is s1 because s0 is taken to be 0. x2 is s2 minus s1, etc. xn is sn minus n minus 1. So therefore x1 is equal to s1, but for general n, xn is the time of occurrence of the nth event minus the time of occurrence of the n minus 1th event. So from that you can easily see that x1 is nothing but the time to wait till the first arrival, and for n greater than 1, because it's sn minus 1, this will be the time to wait for the nth arrival after the n minus 1th arrival, because sn minus 1 is subtracted. So the question that we're going to ask is, remember we already have obtained the joint distribution of S1 S2 Sn. We obtained the joint density. It's not clear to us what the joint density, where it comes from, but at least we have the joint density. So from that we are going to ask, what is the joint distribution of the sequence xn? Clearly x1 is s1, so there is no question about that. Therefore x1 has the same distribution as s1, which is exponential lambda. To find the joint distribution of x1, x2, xn, we note that by definition of xn, s1 is x1, s2 is x1 plus x2, etc., and sn is x1 plus etc. up to sn. So essentially the sk's are the partial sums of the x sequence. Now we know already that the s1 s2 sn vector has joint density given by this. This is something we have just proved. Using the very well-known Jacobian rule, one can find the joint density of x1, x2, xn. You can easily see that if you do this, apply the Jacobian rule, which is a standard thing in probability, basic probability, you can find the joint density of x1, x2, xn, and you can see it turns out to be this. But this is much nicer. You see the joint density of x1, x2, xn is this function g of x1, x2, xn, which is a product of the functions lambda into e to the power minus lambda xj for x1 greater than 0, etc., xn positive. So clearly you can easily see what this means is that not only is that all the xj's are exponential random variables with parameter lambda, but they're all independent because the joint density is a product of the marginal densities. Of course this is true for every n. So we conclude that the entire sequence xn are basically nothing but IID exponential lambda random variables. As an immediate consequence, of course, since xn is the sum of n many IID exponential random variables, and this is a very standard result, Sn has to be the gamma distribution with parameters n and lambda, which means that Sn has this density. Of course, you could have obtained it from the joint density of S1, S2, Sn also by integrating out other variables, but this is a direct way of finding it. Okay, so the result that the inter-arrival times of a Poisson process with parameter lambda or rate lambda or IID exponential lambda gives a very useful and important way of looking at a Poisson process with rate lambda. What it says is that in a Poisson process with rate lambda, the successive arrivals occur in the following manner. Start with no arrival at time t equal to 0 and wait for an exponential lambda time for the first arrival. After the first arrival occurs, now you have to wait from then on for another independent exponential lambda waiting time for the second arrival, and so on. By that I mean that after the second arrival has taken place, again you have to wait from that time point onwards for an independent exponential lambda time for the third arrival, and so on and so forth. In general, every time an arrival occurs, you have to wait from then on for an independent exponential lambda, independent of everything that has happened so far. So for an independent exponential lambda time for the next arrival. And these exponential lambda waiting times are all independent. So this gives a much clearer picture or a different picture of how to think of a Poisson process. But the important part is, we will see that in our next module, you will see that this description actually gives an alternative definition of Poisson process with intensity lambda. Remember, here we started with a certain definition of Poisson process and then derived this as a result, but we are going to show that we could have started with this and obtained the original properties of Poisson process. So in this module, we began with the definition of what is called a general counting process, which was basically a sequence of arrival times, random, and then based on certain assumptions on the sequence of arrival times, very elementary assumptions, we were able to define a counting process. But then quickly we defined a very special kind of counting process, namely what is called a Poisson process with rate lambda. And then we, after the definition, we defined what are called arrival times. We found the distribution of the arrival times for a Poisson process. The definition of a Poisson process was not through the joint distribution of arrival times, but starting from whatever definition we gave, we finally were able to find the joint distribution of arrival times. But what is more important is, for a Poisson process, we saw that if we look at the inter-arrival times, that is times between the successive arrivals, those turn out to be IID exponential random variables, and that is going to be a very crucial part in handling a Poisson process.